Welcome, everyone. We wish to acknowledge this land on which the Fiat Institute operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still a home to many indigenous people from across the island, and we are grateful to have the opportunity to work on this land. Our speaker today is Wade McDonald, a next generation member, and Wade is a PhD student in computer science, working with Professor Nathaniel Osgood in the computational epidemiology and public health informatics lab, Cepheid Lab, at the University of Saskatchewan. His PhD research is focused on informing epidemiological simulation models with wastewater surveillance data. Wade previously studied civil engineering and holds 10 years of teaching experience at the University of College of the North in the past. His research interests include simulation modeling and cross-disciplinary applications in computer science. Today, he will be presenting their work on an overview of agent-based simulation modeling with examples. Wade, the floor is yours. Thank you for coming.
Thank you. So just a moment while I get my slides up.
Sure.
All right, is that visible?
Yes, it is.
Thank you. So thanks for that introduction. I'll begin by also acknowledging that at the University of Saskatchewan, we acknowledge that our main campus sits on Treaty 6 territory and the homeland of the Métis. We pay respects to the First Nation and Métis ancestors of this place and reaffirm our relationship with one another. So an outline of what I'll discuss today, a brief introduction. I'm going to talk about what is simulation modeling, and then I'm going to look at two examples. One is a pertussis model, and the other is chickenpox model. And I'll briefly say something about COVID-19 and the work our group has done on that, and then we'll conclude. So about me, this was kind of covered in the introduction, so I don't need to really go through it at length. The Computational Epidemiology and Public Health Informatics Lab, or CEPHL, is located at the University of Saskatchewan. It's led by Dr. Nathaniel D. Osgood, who is my PhD advisor in the Department of Computer Science at the University of Saskatchewan. So it's focused on applying computer-based simulation models, mobile technologies, and big data to understand public health outcomes and policy trade-offs at a population scale. So Dr. Osgood is a computer scientist, but he has many years of collaborating with healthcare professionals. So I'll talk now a little bit about what simulation modeling is for those that don't know. So these are computer simulations of complex systems. They play out over accelerated time. And these are, as any model, including statistical models, these are an approximation, but one that can provide learning through its construction and application. Compared with statistical models, these are generally much more detailed, but have a greater computational burden to evaluate them. So why would we build a simulation model? Mainly as a learning tool. We can also, as part of this, we can also use it to encode a complex hypothesis, so it can be shared, subject to scrutiny by others, and be tested scientifically. We can use models to run what-if scenarios given our assumptions about the system. Some benefits of doing a model study is that it is less expensive than real world experiments. There's no risk to life or health because we're dealing with simulated people and simulated environments. Fewer ethical issues since real humans are not involved. And it's faster. We can test ideas that would play out over years or decades in real life. Agent-based simulation models are one methodology of constructing simulation models. In these models, agents are placed in an environment. The agents are autonomous, which means they can act independently of each other. They're unique. They can have characteristics that differ from agent to agent. And they interact locally, which basically means that they don't have to interact with all the other agents or the entirety of the environment. They focus on their immediate surrounds. Agents can retain a state that can include history. And our concern in constructing this is to observe emergent behavior of the system given our model assumptions. Some advantages of agent-based models is it's quite simple to implement representation of heterogeneity. The agents can be individually characterized, and the local interaction allows for things such as network effects that aren't captured in other modeling methods. Some disadvantages include that it's computationally intensive and the compute requirements scale with the population of agents, sometimes superlinearly. And it's often, at least with current tools that are available, it's less explainable to non-modelers what exactly is going on in the model compared to some other methods. So here's a screenshot from a model. So the agents in this one are the people, and you can see those red clouds around some of them. They are infected and they may spread, they may expose other people within that radius. And when running this model, these people move around and interact with each other over time. Some of the tools that are available for agent-based modeling, the first I'll mention is AnyLogic. This is the one that is currently most used by CFL, and it was used to construct the example models I'll be discussing this afternoon. Some other fairly popular ones include Repast and NetLogo, but there are quite a few softwares as listed on this Wikipedia page used for this type of modeling. So this is out of order with my outline, but first I'm going to talk about a chickenpox model that I participated in building using AnyLogic. So the principal investigators on this project were Dr. Alexander Doroshenko, Dr. Mara Farag, and Dr. Nathaniel Osgood, my supervisor. Students include Ellen Rafferty, who is now, she's now got her doctorate, myself, and Winchell Chen, who is about to defend his doctoral thesis. So chickenpox and shingles, a bit of background on these diseases. They're both caused by the varicella zoster virus, or VZV. Chickenpox is generally a childhood disease, but once you've had chickenpox, the virus remains dormant in your body and it can reactivate later in life as shingles, which can be an extremely painful condition. So our initial research question with this model was, does vaccination for chickenpox cause increased shingles incidence? Some key features of the model: we used a user-defined network of 500,000 agents, an open population, meaning people are born, age, and die within the model run, a preferential contact age, different connection range for each disease. Chickenpox is quite contagious, being airborne, whereas shingles, I'm told you pretty much have to touch the rash to catch shingles or chickenpox from a person with shingles symptoms. A bimodal population density as well. So it was a stylized arrangement, but we had a square space with a densely populated urban core surrounded by a sparsely populated rural area. So this represents the state chart, and I'm not sure where I can you see my cursor as I point on here?
Yes.
Thank you. So this is a representation of the natural history of the disease. And what these charts are is it's a mutually exclusive and collectively exhaustive group of states that the agent can be in with respect to, in this case, chickenpox and shingles disease. So you can only be in one of these at any one time, and each agent can be in its own state with respect to this chart. So there's a susceptible, maternal antibody state, susceptible. There are two vaccinated states because there are two doses for the vaccine. The first one allows a breakthrough infection, which will result in a weaker infection than the full-blown disease. Then you can be infected and infectious is represented by this state, and then afterwards you can remain symptomatic but no longer be infectious. Then the recovered chickenpox state is compound state. So basically you would start in recovered chickenpox. If you're exposed to chickenpox after recovering, you can be in a state of being boosted immunologically, and that delays your susceptibility to shingles. And then later on in life, at a certain rate, you can get shingles, which has two forms of symptoms. Post-herpetic neuralgia being the severe one that we probably hear about from people who've contracted it, and then a post-recovered from shingles state, and a small chance that you can get it again afterwards. This is another state chart in the agents, and this is for life and death. So people begin alive, clearly. They have a certain rate of death based on age outside of the model disease. And then there's these internal transitions will occasionally happen while they're in this state. So one of them represents reproduction, pregnancy, and the other one simply updates these variables every now and then, which control the other rates. The message transition here represents death from chickenpox or shingles disease, which is highly unlikely, but it's known to happen. So we fit this model to the age distributed incidence of chickenpox and shingles in the pre-vaccination era. So this is for chickenpox, and here's for shingles. The red being the reference from literature and the blue being model output. So what we found, this graph represents a paired run. So the yellow is with no vaccination, and the green is with chickenpox vaccination beginning at time 0 right here. We use a burn-in or warm-up period for the model of 100 years to stabilize the behavior. And then beginning at time 0 with vaccination, this is plotting shingles cases on the y-axis. So we actually see an increase in shingles before it decreases following the introduction of the chickenpox vaccine. So this was our key research question. Now, some of our model assumptions are not well defined, especially how strong the boosting effect that I discussed when you're recovered from chickenpox is. So this series shows from the upper left a very small effect of boosting through to the bottom right, which is a large effect of boosting assumed. So while we do expect an increase in shingles incidence, the actual magnitude is highly dependent on the assumption about boosting. So some of the outcomes of this model, we actually published 3 papers from this model. One was the effect of chickenpox vaccination on shingles. Another examined optimum vaccination schedule for chickenpox, and a third examined cost effectiveness of various vaccination schedules. The next model I'm going to talk about is simulating pertussis, also known as whooping cough commonly. So this model was done using a group model building process. The principal investigators were Doctors Alexander Doroshenko and Nathaniel Osgood. And then the model builders included Dr. Carson Hempel, who's a postdoctoral fellow working with Dr. Doroshenko, and myself working with Dr. Osgood. And it was further overseen by this advisory panel. The modeling process was envisioned as an extension of a paper published by Doroshenko and others in 2016. The primary model builders, so myself and Dr. Hempel, worked independently on this and coordinated with weekly video meetings, and then met with our local co-principal investigator to discuss progress and issues. We had occasional 3 to 4 day intensive work sessions where one of us would travel to the other location and work on it intensively. And then there were approximately quarterly meetings with the advisory panel to discuss progress and get advice from them. So some key features that we included in this model was a tile-based space allowing for varying population density, a distance-based network, as well as schools and households being contact venues, which I'll say a bit more about in a moment. A data structure was used to optimize range searching, which I won't go into too much detail on that. And it was a continuous representation of immunity state. So we didn't use a state chart as in the chickenpox. We actually used a continuous value that would decay over time and increase when exposed to the pathogen. So this figure represents the networks in which people were connected. So the yellow would be a person of interest, and then the other circles are other people. This person would be connected to all the people within a certain radius of them, as well as being connected to everyone else in their household, which is the square boxes. And furthermore, the blue square boxes represent schools, and children will be connected to other students in the school that they go to. So this resulted in some emergent contact patterns, which we fit to a study called Polymods done in Europe, which was a large study examining contact rates in multiple European countries. So our main health research question with this model was, can immunization of expectant mothers in the 3rd trimester of pregnancy reduce incidence of pertussis in infants? And our finding was that given the assumptions, it can significantly reduce pertussis incidence in the 0 to 2 month age group, which is the greatest risk group for this disease. So should we do it in terms of immunizing expectant mothers? Maybe. The model doesn't tell us about safety. We rely on clinical researchers to make those kinds of determinations. Vaccination during pregnancy may be a tough sell to some expectant mothers in terms of convincing them that it's a safe and effective thing to do. And then in Canada, especially, and other single-payer healthcare systems, it's a question of, will the healthcare system cover the costs? Because if it doesn't, there'll probably be very low uptake. So our model suggests this appears to be a viable strategy, but the question is open whether it's the best strategy for in terms of opportunity costs. But this is actually now beginning to be done in many jurisdictions already, based on other evidence. I'll now briefly mention COVID-19, because that's what everyone's got on their mind during this pandemic. So what did our group do for COVID-19? A number of members of CFL, including myself and Dr. Osgood, were seconded to work with the Saskatchewan Health Authority during the early months of the pandemic. We constructed multiple simulation models, including an agent-based model, which I spent a lot of time working on. We used these models to attempt to anticipate the spread of the disease and the needs of the healthcare system and the people based on this. And we examined what-if scenarios for mitigation of the pandemic. So I'm limited in what I can say in detail about that work, but my main takeaway from my experience with this was that science communication is very important, and it's probably something that we as aspiring scientists don't get in much formal instruction in. And I think if I had to do that over again, I would probably change the way I communicated with other scientists and with non-scientists about what we found using the models. So if the idea of agent-based modeling interests you, there are a couple of training sessions called boot camps that Dr. Osgood is putting on So one is agent-based and hybrid modeling bootcamp and incubator for health and healthcare. This runs from August 22 to 27 this summer. And you may attend in person or remotely. The in-person sessions being at the U of S in Saskatoon. And then another one potentially of interest is on systems and data science. And this one runs in June 27th to 30th this summer, again, in person in Saskatoon or remote attendance will be possible. So I'd like to thank you for your attention today, and I'll turn it back to our host. And if there are any questions, I'd be happy to address those.
Thank you so much, Wade, for that great presentation.